Hello and welcome. Today in advanced programming we're going to talk about recursion. Now if you don't understand recursion at the end of today's lesson, that's fine. And if you don't understand recursion ever, you can still probably be a fairly competent software developer because recursion is pretty complicated. But luckily the applications where recursion is actually useful are also pretty limited, and in most of the cases where recursion is the best solution, the solution that doesn't use any recursion is also pretty good and usually a lot easier to write. So unless you're aspiring to be one of the best, it's okay if you don't get recursion even by the end of this entire course. But it is going to help you a lot with some of the solutions that we're going to look at later. With certain data structures, the recursive method of going through them is a lot easier than the non-recursive. So first let's look at what recursion actually is. Recursion is simply a function that can call itself. And the reason that we do that is because we're basically creating an alternative form of looping. And you might say, well, I've already got while loops, I've already got for loops, why do I need another form of looping besides those? Well, sometimes the while loop and the for loop solutions require you to come up with a stopping condition that renders them really inelegant. This is true in problems that fan out mostly, so in problems that go an indeterminate depth. The most canonical example probably of solutions that are tailor-made for recursion is something like getting me all of the files inside of a folder, including the ones that are inside of the folders inside of that folder. Think about how you might write that as a for or a while loop for a second and realize that that's going to be really difficult because every time you run into another folder, you've got to go inside that folder, and every folder you run into inside that folder, you've got to go into that one too, and into those, infinitely until you get to the files. Then you add those to the list of whatever, to the files that you found, and then you have to go back up in any of the other folders that you found along the way. You have to do the same thing, and you have to make sure that you don't visit any of those subfolders twice and count their files twice. So it gets pretty complicated pretty much right away. But we're going to look at some simpler examples first. First we're just going to count to 10 without looping, which is not a particularly interesting challenge, but let's do it. So we're going to count backwards from 10. I've put 10 as my argument here already. And we're going to stop when we get to 0. So when we get to 0, we are done. We're going to stop. I'm going to return in. I don't need to have an integer return type here, but I'm going to do it. Alright, so what do I want to do next? Well, I'm going to save the intermediate value so that I can print it two ways. We don't have to do this, but this is going to be something I'm going to do. I'm going to call the count function inside the count function. What am I doing? What is this? Does this work? Let's run it and see if it works. Well, it doesn't crash. It terminated. Okay, let's print and see if we can count to 10. Alright, I'm going to just print n here. Alright, so I'm printing out n. And I counted backwards from 10. So what happened? Well, main method runs count. Count with a value of 10 gets pushed onto the stack. It's not 0, so we go on from here. It prints, and then it executes count with an input of 9. Okay? Count with an input of 9 gets pushed on the stack. We get back up here. It doesn't return because it's not 0. It prints 9. It gets to here, and count with a value of 8 gets pushed onto the stack. So we could say that this is pushing on the stack because none of these have gotten to their return statement. That very first one, that 10, it got to this count here. It did not reach its return statement yet. Only when that count of 9 returns can the count of 10 return, and so on and so forth. So we can view that by making another print statement here. After that count returns, this one is about to get popped off. Technically, it doesn't get popped off until it reaches that return, but it's about to get popped off. So let's print it. Popped account off the stack. Yeah, that's good. All right. And what will that do? Well, that will count the other way. So we're pushing on the way up, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. And then we're popping on the way back up. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And so we can either count backwards or forwards, depending on whether or not we want to do our work, in this case the work of just printing, before or after the recursive step. And there's actually a name for recursive functions that do all the work in the last step. If the return statement is the last statement in the recursive function, so if you have something like this, then we call that tail recursion. If it's not, then we usually just call that regular recursion. Sometimes we just call that recursion. Actually, no one will call it regular recursion. We just say recursion, or sometimes people will call it non-tail recursion. So if you hear the term tail recursion, that's just a fancy way to say that the recursive part is the last thing that happens in the function. So it does all of its work, and then it recurses. And basically the difference between tail recursion and non-tail recursion is whether it's doing its work before or after the recursive step. So whether it's doing the work on the push or whether it's doing the work on the pop, I guess, is the primary differentiator there. Although really it's just that the recursive statement is the last thing in the function. So that's the only definition you really need to remember for tail recursion. Okay, so we've managed to count to 10 without looping. An interesting novelty, but let's move on to something a little bit more fun. Let's print out the Fibonacci. We'll print out the Fibonacci sequence, and we'll also print out the nth Fibonacci number. So if you're not familiar with the Fibonacci sequence, it starts with 1, 1, and then you add the previous two numbers together, and you just continue to do that. So 1 plus 1 is 2, then 2 plus 1, now those are the two previous numbers, that's 3, 3 plus 2 is 5, 5 plus 3 is 8, 8 plus 3 is 13, 13 plus 8 is 21, 21 plus 13 is 34, and 34 plus 21 is 56, and that's as far as we're going to go. So let's say I wanted to print out the 15th Fibonacci number or something. Well, it's obvious that there is no solution that doesn't require you to generate every other number in the sequence first, or at least that's intuitively obvious. That's actually not true if you have some math cheat codes, but for those of us who are normal people, we know that if we wanted to get the 15th number in the sequence, we would just have to go through and sum up 15 numbers this way. So if that's the case, right, then how do we get the 15th Fibonacci number, or how do we get the 5th or the 10th or whatever? So let's write that function first. And let me call it before I write it, actually. Let's do int, we'll call it nth, and let's go for the 5th Fibonacci number first, because it should be easier to parse. And we'll say n equals nth fib number. We'll pass that nth in there, and I'm going to use this other variable called depth in order to illustrate how deep the execution stack is going. So you don't need this depth variable, although in many cases recursion is easier when you track the number of iterations of depth. In fact, a lot of the time it's how you determine when you're going to stop. You go a certain level of depth. This is true for a lot of mathematical functions that use recursion. You go to a certain depth because each generation of the recursive function gives you more and more precision on whatever math operation it is that you're doing. But you don't want to go on forever because you'll go into stack overflow and all those other nasty things. So you just go to some preset depth and you deal with whatever level of precision you have at that depth. The other alternative for those kinds of mathematical functions that get more and more refined in every generation, for example, there's a function for finding the square root that's very common, a good application of recursion called Newton-Raphson. A lot of those functions will stop when they reach a certain level of precision, so when it's within 0.01 or 0.001 of the real answer, you can stop. But depth is an easy way to stop, and here we're not using it as a stopping condition, we're just using it to illustrate how deep the execution stack is. So remember to keep this execution stack from the count in mind, that this one pushed 10 versions of count onto the stack and then pop them off one at a time. Let's see how many versions our Fibonacci function pushes on the stack and then pops off. So if n is less than or equal to 1, then we have finished, because that's the last couple numbers in the sequence there, so we're done. We're going to go from 5 and then count down until we get to 1, at which point we know that we're done. So here I'm going to write the recursive step first, and then I'll write the printout function after. So let's make this a nice clean tail recursion. That's going to be the nth fib number of n minus 1, and I'm going to also add 1 to the depth to show that we've done a layer of recursion here, and it's going to be that plus n minus 2. Now this is a very strange answer, you might say, and I don't expect anybody to understand this intuitively, so let's print it out and take a look. And I'm going to cheat a little and copy the print statement from my notes because it's kind of annoying to rewrite this. All right, here we go. So I've computed the same sum that I just did for the recursion down here. So the sum of the n minus 1 and n minus 2 there, it's going to print out sum of n minus 1 and n minus 2. It prints out what the actual value of that is, and then it prints out the depth. So let's let this thing ride at 5 and see what happens. Okay, so in the first generation, let's write this out in a little comment here. In the first generation, when I passed 5 to the function, right, the print statement there did the sum of 4 plus 3, and that's of course equal to 7. That's the first layer of depth. I'm printing before I do the recursive step, so I'm printing before I push the next layer onto the stack. Then I get to 3 and 2. 3 and 2 is 3 and 2 is 5. And then I get to, well, first let's talk about where the 3 comes from. Okay, so the 3 is actually coming from this number 4 and its next generation. So the recursive function has to recurse first for that number 4, and that recurses into this 3 and 2, 4 minus 1 and 4 minus 2. Then the 3 is going to have to recurse again into 2 plus 1. We're going to end up with 3. And then the 2 has to recurse to 1 and 0, where we end up with 1. And then this condition is met, and we start popping all the way up. So at this point, we pop, pop, pop. And we pop up to the point where this 1 returns, so we don't have to worry about that one. That will be the next one, actually. Sorry, we do worry about it. So it pops up to the 2, and this is why recursion is hard. It's very difficult to keep straight. I even have notes, and I'm still... Alright, so it pops up to the 1 up there, this 2 up here at depth 2. Gosh, let's mark out the depths as well. Maybe this will help me keep track of it. Alright, so depth 1, depth 2, depth 3. Okay, so when we got to this 2, we had one more iteration to go. That brought us to depth 3. And then we're done because we reached 1 and the condition is met. Now we're going to start popping our way back up. This 1 doesn't need to be processed, as I originally said. Sorry for the confusion there. But this 2 that we hadn't processed yet, because remember we processed the 3, we hadn't processed the 2. The 2, which is here on that right-hand side, that second statement, that one's going to have to get processed now, and that's where you get this at depth 2. So this 2 was at depth 1, which means that the the next step would be at depth 2. That gets popped off, which leaves us to process this 3 that we hadn't addressed. The 3 gives us a 2 plus 1 back at depth 1. That 3 was at depth 0. And then there's still more to be addressed. There's the 2 here. So we need to go one layer deeper and do the 1 plus 0 step back to depth 2. All right. Confusing, very much so. But did it get me the right answer? Let's have a look. The and fib number is... Well, that ruined my cool comment. I'll leave that for now. The nth fib number is 5. Is it? Okay, the 5th. 1, 2, 3, 4, 5. It is 5. All right, awesome. Let's try for a larger one. Let's go for the 9th. What's the 9th? It should be 34, right? And it is indeed. But look at how many layers of execution we had to go into. I'm not even going to try to explain this one because, boy, howdy, look at that. We go 7 layers deep at the peak at some point in this recursive function. That's really difficult to follow, isn't it? Let me erase the note here. This is a really inefficient recursive function, so you could actually probably write a much better iterative function to calculate the Fibonacci number than this. And the reason it's so inefficient, let's go back to the example with 5 for a moment, is that it recomputes the same values many times. It does 1 and 0, 1 and 0, 1 and 0 3 different times because it doesn't preserve them. And it should be pretty obvious that as you go to this left-hand side, the n-1 and the n-2, that they're going to significantly overlap because everything that goes to the n-1 side, well, in that generation, it's going to have another n-1 on the left-hand side. And that's going to be exactly the same set of numbers as this right-hand n-2 was in the previous generation. So basically, you do every pair at least twice, and you can see that here. Other than the very first set of numbers, pretty much every pair gets done at least twice. So the only one that didn't was the 3 and the 2 there. And if you expand it out to another generation, we'll see some things getting done 1, 2, 3, 4, 5 times, or 6 times. And that'll keep getting worse and worse the more generations we add to it. So let's look at a slightly better Fibonacci number sequence generator. This time we're also going to print out the sequence for fun. So let's comment this one out and call the next one. I'll write the call for it first. Let's go with int n equals, let's call it something else, int fibby equals fib. And then this one requires you to start it out. So I'm going to take the 1 and the 1 as an argument. This one's going to pass the last 2 numbers in every generation into the next generation. This uses up a little bit more memory, obviously. This one only takes 2 numbers in each generation, but only passes 1 in the function. Remember, we don't actually need the depth. We're just using that to illustrate. But let's see if we can pull this off with less function calls, which is a priority because less function calls means it's probably closer to O of n. This is probably closer to O of n squared because the number of function calls seems to be increasing quadratically with the number that is given for the n, for the nth Fibonacci number. All right, so we're going to first compute the sum. We don't actually need a C here, but it's much easier to think about this and conceptualize it with a C. You can actually do it with just the 2 variables, but I'm going to use a C here because it's much easier to keep in mind. And you'll note that in the next generation, so after we add 1 and 1 together, okay, the sum is 2, and then if you consider this to be A, and this to be B, and this to be C. That's the first generation, right? And then in the next generation, this will be A, and this will be B, and this will be C. Right? And then in the generation after that, this will be A, and this will be B, and this will be C. And we just continue on like that. And so all we have to do is have A take B's place, B takes C's place, and then we return the sum. Now, you would note then that you don't actually need B. B is actually, or sorry, you don't actually need C. B is actually moving up in every generation, and B becomes the sum, and so C is kind of an extra there. But we'll keep it again. I think it helps with clarity. So A equals B. A moves up and takes B's place, and then B moves up and takes C's place. Another reason why C helps here is because you need a temporary value to perform this swap anyway, so you might as well just keep the temporary value that you use to perform the swap. And here we'll demonstrate another example of how we might terminate our recursion. So this one terminated when it got to the bottom, and it terminated when it got to n equals 1, and it started at a high number. This one will go the other way. We'll terminate when we get to the first Fibonacci number that is over 1,000. So if the Fibonacci number that we've computed so far is not over 1,000, then we will just recurse again, and we'll add 1 to that depth counter so that we can keep track of how deep our stack calls have gone. Now I want to also print out what's happening in each generation, so once again I will cheat and copy from my notes and print out the values of A, B, C, and depth. And then the last step is to return the actual value that we've computed at the end here. All right, let's check this one out and see. First thing you'll notice is that at depth 14, which is pretty impressive, it's calculated what seems to be a very large Fibonacci number. We left off at 3455, and then it goes to 89. It looks like we're off by 1 here, first of all. That's interesting. So either my math, oh yeah, my math is off. 34 plus 21 is 55. Okay, whew, function's good. My math is bad. So 55 is the correct number there, actually. All right. Yeah, we got to a depth of 14, and we're at a number that's way further along than we had sketched out before, like 89, 144, 233. This continues on for a while. Let's bring back the other one that we had figured out and see how many stack pushes, how many functions get pushed on the stack to calculate. I think this is the 14th or 15th Fibonacci number. Let's see. Nope, actually that's 370s. Okay, 14, 15, 16, 17th Fibonacci number. Okay, how many pushes do we need? Look at how many the other function needed to compute exactly that same answer. It took thousands. And this should demonstrate to you the difference between a solution that's O of n, like the one that we wrote down here, and a solution that's O of n squared. And boy, is this one O of n squared. It got huge for only a depth of 17. Now technically I don't think this one is O of n either. It's slightly worse than that, but it's not as bad as this one. Whatever the quadratic power is for this one, it's much larger than whatever the quadratic power is for that one. But I didn't exactly figure that out, and it's harder to figure out the big O power of recursive functions because it's so difficult to follow along with their depth and everything. Okay, so that one's pretty bad. This one's okay. Let's change this one then to terminate at some Fibonacci number so that this one works the way that the first one worked. That it allows us to get, let's say, the 10th or 12th or 17th number. Well, one way to do it is to use that depth variable, which in this case you might have noted is the Fibonacci number that you're getting. So this was the 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 15th Fibonacci number. Actually, the function that we wrote here excludes or this one excludes that 1 from the count. So when it actually gives you the 5th, I think it's actually giving you this one includes 0. That one actually starts at 1. So when it gives you the 5th, it's giving you the 1, 2, 3, 4, 5th, rather than the 0, 1, 2, 3, 4, 5th. So if we counted the same way, this would actually be the 17th number down here, I think. All right, anyway, how do we determine a stopping point so that we can make it work similar to the other one? I'll even bring back that nth variable here. Well, one kind of lazy way to do it is to pass in the stopping argument. We can pass in stop depth like this, and we can pass in the nth there. And we can stop instead of when c is less than 1,000, we can stop instead when the stop depth is exceeded. So when the depth is greater than or equal to the stop depth, we'll stop. And we could have made the stop depth a global variable instead of awkwardly passing it, because now it has to be daisy chained along to every other recursive call here. That's kind of weird, isn't it? And that doesn't seem correct. What do we got here? Oh, other way around. Flip my equals there, and there we go. Now we get to the 18th number. So you get the idea there. It's one higher. I should probably go stop depth -1 then in order to stop at 17, but there you are. We're stopping at a certain Fibonacci number now instead of stopping when it exceeds 1,000. So again, one way that you can get your recursive functions to stop. Alright, so that's it for the kind of simple examples of today. What we'll look at now are a few examples of some kind of recursive-based art and some examples of where recursion enables you to do some pretty cool things without having to loop. So let's move on to that demo. The first one we're going to look at are these lovely infinity squares. The infinity square is so called, let me actually show you before I show you the code, because when you click, it makes an awful gosh darn lot of them. And what it's doing when you click is that it's creating one square. And then that one square is creating a certain number of children for itself. And that's what this variable up here determines. How many children is each square going to spawn? Because that square's children also make 2 children. And that square's 2 children also make 2 children. And so on and so forth. And it continues to do this until these squares are a certain size. So each next generation of children is slightly smaller than their parent, and each generation of children continues making more children until they reach the minimum size. And here I decided that the minimum size would be 5. So the squares get smaller and smaller until they hit a size of 5. Now they start at, I don't remember, but let's have a look. They start at 50, and then they stop when they hit a size of 5. That means that there are 5, 45, 40, 35, 30, 10 generations, or 9, since I stopped at greater than rather than greater than equal. There are 9 generations of children that get spawned off of that first square. Each one is currently spawning 2 children. So the first square in the first generation has 2 children. That gives you a total of 3. Then each of those 2 has 2. And that's 4 in that next generation. A total of 4 plus 3 is 7. Then each of those 4 has 2. That's 8. 8 plus 7, and so on and so forth. Let's change it to just a single child per square. Now we should see 9 or 10. There we go. And you can control this variable here to make them spawn a little bit closer together. Alright, let's look at the relationship between the first square and its children. Now each of the children has a line drawn to it from the parent. So that's the topmost square, a child, its 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 child, all the way down. And you can place a few of these infinity squares at once. And you can definitely follow the lineage here pretty easily. Now let's try following that lineage with this explosion of children from recursion here. Okay, well that's obviously impossible. Let's maybe start or finish sooner. All right, instead of stopping at a size of 5, I'm going to stop at a size of 25. And, okay, that's still maybe a little bit too hard to follow. Let's stop at a size of 35. This should give me something like 30, 16. Okay, yeah, these are a little bit easier to follow. So you can see the large square. Try to get a good spawn. All right, here's a good spawn. You see the large square, the very first top-level parent, has 2 children, this one and this one. And then this one has 2 children, that one and that one, for which there are lines to it. And then its other child has 2 children, that one and that one. And then that one has 2 children, that one and that one. And so on and so forth. All right, so I've set up the problem. Why is this a recursive problem? And why is it interesting? Because you can see that aside from the loop that controls the number of children that each square has, I accomplished the spawning of all of these squares without any looping. Okay, so this is just for the 2, so I could just have easily have just called this twice or something. But I wanted you to be able to control the number of children that spawn in each generation. Makes it more interesting. Other than that, there's no looping. What does it do? Well, here in the constructor for infinity square, it calls the constructor for infinity square. It has an array of children that it creates. That array is also an array of infinity square, so an array of the same kind of object that it is. And then it recursively generates those and adds those to its children array. So each square, starting from the parent, as long as its size is bigger than 5, generates 2 more squares and then adds them to its array. I also have this total children counter going here if you wanted to print out how many had been spawned all together in the scene, so you can see how quickly that they expand. Now only that very last generation, the ones that are size 5, have no children, and they set this boolean to false. We'll see that come in handy later when we do something even cooler. All right, let's look at how they can draw them, because how do I collect all of the children in the scene and draw them all? I haven't added them to any kind of data structure. I guarantee you it's not added to anything in display. In fact, the only thing that the display tracks is the single root infinity square, the parent. From the parent, I'm able to draw all of the children because in the draw function, after the square draws itself, so this is the code for it to draw itself, it then calls on its children. It loops through its array of children and orders them to draw. The children then execute that same code because they have the same draw method. They are exactly the same object. And then they loop through their children and call draw on those children. And then their children run the same code, and then they loop through their children and call draw on their children. And so you're able to have all of this happening from only a single reference to an object, because you have this structure where recursively you're able, through that connection to the child objects, draw all the other ones in the scene. Let's look at a more interesting example. These particles not only draw themselves to the screen, they create themselves the same way the squares that we just saw create themselves. They also have the ability to have 1 or 2 children. But in addition to being able to draw themselves, again the same way, they can also move around. And they move around by bouncing off the side of the walls. When they reach one of those walls on the side of the panel, they bounce. So that's what these 2 parts do. But they also move with gravity, so you'll see the velocity increase when I actually run this demo in a second. And like with draw, I was able to write the movement code for each of them individually. And then instead of storing them in some kind of list and calling move on each one of them in the scene, I was able to call move on just the root object, just that topmost parent, and then the parent tells all of the children to call its move function, those children tell their children to call the move function, and so on and so forth. So, what's the finished product look like? You get this very nifty particle simulation where they change color as their position and velocity changes. They're also all able to accelerate towards these little black holes that you can spawn and then remove, and then they start moving as normal again under the effects only of gravity, and you can have a few black holes in the scene at the same time. These aren't very good because they attract things not in like a circle around them, but in a square, but you get the general idea. Look at how many particles there are on the screen, and I can spawn even more, depending on the power of your computer and whether or not you decided to turn on anti-aliasing when you ran this. You can actually get to quite a few before the simulation starts to bog down. And all of this is being done with only 4 calls to draw, basically. I hit the right click to spawn these things 4 times. The draw is technically only being called 4 times from the display method, but then each of those parent bubbles is calling the draw method on their children, and they're calling it on their children, and so forth. Okay, let's go on to what I think is the coolest example of drawing a fancy spiral. Now, just like the 2 kinds of particles, the spiral draws a circle, and then it spawns a circle. It is a circle, and it has a single child. This one doesn't have multiple children, so this one might be a little bit easier to see why recursion is interesting when you're not able to loop, because this one doesn't have any looping at all. It only has 1 child. And the next child, its position is determined by rotating some distance away and moving some distance away. So imagine that you've got some point, and then you want to spawn the next child, a little rotation away, and a little rotation for the next one, and a little rotation for the next one, and a rotation for the next one, and eventually you end up spiraling out. And you can change the rotation that children spawn away by changing the theta step, which is how far each child is rotated away from its parent. And by changing it, we'll see a couple different things happen with the spiral. And I should have said epilepsy warning, major epilepsy warning. This thing is flashy. In fact, let's change it from a strobe mode to just plain colors for now. And then we'll bring back the strobe. The strobe is very amusing. So depending on the rotation, this also changes the color. And that was pi over 6. Let's try pi over 8. You get a very different spiral depending on how much you rotate in each recursive generation. Here's pi over 10. Look at that. And you can even play with funky numbers that have nothing to do with pi. So here's 90, and that one I find very amusing. Oof, look at that. Now the other cool thing that you can do is that you can invert the lineage of the spiral. What does that mean? Well, you can see that this is an innie spiral. The big guys start at the top, and then it spirals inwards from the big guys. You can invert the lineage so that it becomes an outie spiral. You know, you could actually flip those, but whatever. The outie spiral starts small and then gets bigger and bigger and bigger. It kind of looks like an ice cream cone. The other thing that you can do here is if you set the strobe mode to true, you can change the way that the colors strobe by increasing theta. Here I'm going to flip it, and then I'm going to change the theta increment. And you'll see that the pattern of the colors on the spiral changes as it animates. If your computer is not running slowly, it should go at about 30 FPS. I think I'm getting a slight frame drop here, but you can still see the characteristics of the spiral changing as the increment moves up. And as the increment goes to some pretty cool values, let's see. Yeah, we get some really hypnotic effects going. Ooh, hypnotic. All right, let's look at what that step is actually doing. So when the spiral draws itself, very similar to the way that the circles and the squares drew themselves, it draws itself, and then it recursively draws its children. But in the step where it draws itself, I have this static variable called strobe. And strobe moves up and changes the characteristic of the red color value. And then when the child goes to draw itself, it picks a slightly different color because the strobe is static. And in each generation, I'm adding some value to the strobe. So the next circle in the spiral gets a different color, and then the next one gets a different color, and the next one gets a different color. And then depending on how close together the circles are and the amount of rotation that they had when they were spawned, sometimes those colors line up, and you get these strobe effects that seem to be in sync. So as the theta gets to in sync with the way that they were spawned in, you get those kind of very synchronized, flowy looks to the way that the spiral animates. Okay, so we looked at recursively generating a spiral by spawning child circles from a single parent circle. But let's look at how this inversion of lineage works. First of all, let's knock out all of the features that are available here. So there's that has children variable, which is only false for the very last node, which has no children. So the very last, the smallest node spawned in the spiral, that's going to have no children, and it ends the recursive spawning of more nodes or circles, or whatever you want to call them. Every other circle has a child. The only circle that doesn't have a parent, so the only circle that has children but has no parent, is the very first one, the root of the entire system. So with that in mind, a circle that has children but no parent is the root. A circle that has a parent but no children is the very last one in the sequence. With that in mind, we can now invert the lineage. So if a circle has children, then it's not the last one. Okay, and we always start at the root to do this inversion. So in order to invert it properly, you need to pass in the root as an argument. The topmost parent, we call that the root. So when we've reached the first node that doesn't have a parent, then the recursion is over. What does that mean? So if the node has children but doesn't have a parent, then the recursion is over. We have reached the root. And in that case, we have to set it to have no children, because the root becomes the last item when we're inverting the lineage. The root becomes the very last child. All the other nodes, their child becomes the node that used to be their parent, and then they tell their child to do the same. So the parent, the very last node, has no children. Every other node, its child is now the node that used to be its parent. All right, the last node then is the only edge case that we need to handle. The former last node, the one that itself has no children, that one is going to become the new root. That one now has no parent, because the root doesn't have a parent node, but it now has a child. It has the node that used to be the second to last one. And if, again, that was confusing to you, don't worry about it. But this is a common question that you'll see on interviews, or at least it used to be, because although we haven't covered them yet, what this is essentially a linked list, a doubly linked list. So when we come back to that next week, bear in mind that this is basically how you invert a doubly linked list, which is a very common interview question. Okay, well, that about covers it for the cool recursive art demo. Let's just finish it off with one more awesome spiral for the road, and then we'll call it a day. Look at it go. One tip, if you're running this and you have a slow computer, go to the display and set the I have a good GPU variable to false, and it will help you run this on your otherwise underperforming computer. Okay. One more go at spiral land. Try to get this thing in sync. Beautiful. Okay. Hope everybody enjoyed the recursive artwork, and stay tuned for linked lists very soon. See you next time.